We've spent most of this course talking about really just 3, maybe 4 atoms: carbon, nitrogen, oxygen, and hydrogen. And it's amazing how complex that can be. Just throwing a little bit of boron and silicon, and then suddenly it's hard to know where to push your arrows and where to get started. But throughout the course, we've been talking about sulfur reagents like sulfonyl chlorides and sulfonate leaving groups, and maybe some phosphorus chemistry mixed in a little bit. I don't know, I can't even remember what we talked about with phosphorus. But phosphorus and sulfur chemistry make up a large part of what goes on in organic chemistry and in biochemistry and chemical biology, so it's worth talking about these as individual topics. So we've been talking about phosphorus chemistry, and you have to get comfortable drawing 5 single bonds to phosphorus. That's not normal, right? If you're used to carbon and oxygen, that's going to make you uncomfortable, but phosphorus, no problem. The phosphorus 5 oxidation state has 5 bonds to phosphorus. Now, when we left off on Friday, I had introduced to you this mechanism for substitution at phosphorus 3, PCl3, PBr3, reagents where there's 3 potential leaving groups on phosphorus. What's the mechanism for exchange? It is not SN2. Right? I showed you this chart that explains that under acid catalyzed conditions, you get incredibly rapid rates for substitution at phosphorus 3. And it all starts off with protonation of that phosphine in order to give a phosphoniamine. Once you make a phosphoniamine, it is very easy for nucleophiles to attack. So really the proton adds on there and accelerates all of this exchange. And then the last thing is you pull the proton off and you never would have known it was there. And you're going to see these mechanisms very commonly when you do chemistry with phosphorus 3 substitution. Let's go ahead and take a look at how this really enabled the entire field of biotechnology, still does. It powers biotechnology. How many of you have ever worked with a PCR primer? Or how many of you ever ordered an oligonucleotide on the web? Some of you, right? Where do those come from? Somebody makes those using a machine that is powered by organic synthesis and phosphorus 3 substitution. Right? You could order your own personal machine like a toaster oven and make your own, but usually people just order these online nowadays. And so how do these machines make phosphorus oxygen bonds when you assemble an oligonucleotide with up to 100 new phosphorus oxygen bonds in there? Well, it's based on this acid catalyzed substitution mechanism that we just covered. So the starting material, the subunit for assembly of an oligonucleotide with 50 DNA subunits is this thing called a phosphoramidite. That's this functional group right there. And notice that it's phosphorus 3 with lone pairs here on the phosphorus atom. And so people realized when they were developing this chemistry, Letzinger and Carruthers realized, if I want to have fast, efficient substitution, I want acid-catalyzed reactions. And so they screened probably 1 billion different acids until they arrived at this thing right here, tetrazole. In 1 million years, you wouldn't have guessed that that's the ideal acid here. Right? Tetrazole has multiple functions. It's kind of like DMAP, but it's an acid. And so it's going to start off, you could kind of guess that it's going to start off by protonating this phosphorus atom here, this phosphorus 3, making it super easy for oxygen nucleophiles to attack. Like the end of a chain of DNA, like this. Oxygen nucleophiles like this right here. If you're assembling this long oligomer of DNA nucleotides, and you got 49 nucleotides on here, and you want to add the next one, you want to use phosphorus 3 acid-catalyzed substitution. So they use tetrazole. Look how acidic this is. You could never have known this or guessed this. It's got a pK that's about the same as a carboxylic acid. And that's better than a carboxylic acid, because if you used acetic acid, the oxygen on acetic acid would stay stuck to the phosphorus. Phosphorus loves oxygen. But when you use an acid like this based on nitrogen, phosphorus is not so happy with that nitrogen atom on there. So this acid-catalyzed substitution process makes new phosphorus-oxygen bonds. And the chemistry, because you're doing acidic conditions, is so fast, less than a minute cycled reaction times. How many of you have ever done a reaction, an organic reaction in a chem lab that takes 1 minute for completion? Never, right? So you can get the idea that a DNA synthesizer can synthesize a lot of phosphorus-oxygen bonds in a short amount of time. And the yields over 99%. 99% is not good enough. They've got these optimized to 99.5, 99.7, 99.9% yields. So man, phosphorus 3 is the way to make phosphorus oxygen bonds, but there's a problem. The problem is that you end up with a phosphite functional group that is now sensitive to acid. And if you have some other water molecule floating around or some other DNA chain that has an OH on there, you're going to substitute off everything just as fast as you made that new oxygen-oxygen bond. So this species right here, which still has the lone pair and is still sensitive to acid, is really sensitive to substitution. The phosphite that you generate is super sensitive and labile. And so what do we do to get around that? Once you get your 99% yield, the next step for the DNA synthesizer machine is to oxidize this functional group to give you a phosphate ester. And phosphate esters are rock stable. Right? That's the trick. You make your phosphorus oxygen bonds using phosphorus 3, and then you oxidize it to a phosphate ester, phosphorus 5, and that's not easy to substitute anymore. Now let's go ahead and take a look at the oxidation of phosphorus. I kind of mentioned this before when I talked about two common phosphine reagents that you see used all the time in organic chemistry. Most common is triphenylphosphine. So here are the most common reagents that you see phosphines where you have alkyl groups on phosphorus. Tributylphosphine and triphenylphosphine. And tributylphosphine is a little bit more nucleophilic. But the problem with this, right, tributylphosphine with alkyl groups is a little bit more nucleophilic, but it's super easy to oxidize. Let me write easy here. Easy to oxidize. More than 100 times faster to oxidize than triphenylphosphine. You open the bottle of tributylphosphine, it's already starting to oxidize from the air. Nobody really wants to work with tributylphosphine. So that's why this is the most common. The triphenylphosphine with 3 phenols on there is the most common alkyl phosphine reagent. Now let's go ahead and take a look at the mechanism for oxidation of phosphines or phosphite esters on a DNA synthesizer. So when you make a phosphite ester in 1 minute in 99% yield, you don't want that to hydrolyze as soon as a molecule of water gets into your system. So what you do is you oxidize that using something that has a weak bond, like iodine. That's what they use on the DNA synthesizers. But you could just as easily use hydrogen peroxide. You could use Br2, bromine, which is more corrosive, or chlorine, which is even more corrosive. So iodine is kind of a happy medium here. It's not too corrosive, and it gives fast rates of oxidation. You could use bleach, right? It's got that weak bond between 2 electronegative atoms. And as long as you're doing it in water, right, the end product is going to be an amazingly stable P double bond O. So it doesn't matter whether it's tributyl, triphenyl, trialkoxy, like a phosphite ester. It's easy to oxidize phosphorus to P double bond O to put an oxo group on there. Let's take a look at the mechanism. Now that we've seen this acid catalyzed mechanism, I hope you have an idea what the first step is going to be. The first step is going to be using these phosphorus lone pairs to attack and break that weak bond and push out a leaving group. This is what would happen with peroxide if you have an oxygen-oxygen bond. This is what would happen with chlorine, Cl2, if you had a Cl-Cl bond. And so you make this phosphonium intermediate, right? Just like we did with protonation, you make a phosphonium intermediate that is now very easy to attack. So if you're doing this in water, which is the way the DNA synthesizers work, you've got water present during these reactions, and the water will now come in and make the phosphorus oxygen bond, and that's what the phosphorus really wants. Phosphorus doesn't want this long, lame bond to iodine. It wants a bond, normal length bond to oxygen. I'm not going to show the steps, but you add the water in, and then you deprotonate the water after you add it in. It's not like you're adding in hydroxide. And so the conditions are done, these reactions are done under slightly basic conditions. They add 2 equivalents of a pyridine derivative in here when they have the iodine. I didn't show that as part of the mechanism, but they usually use 2 equivalents of a pyridine derivative called lutidine in here. So the conditions are basic. You couldn't know that. Maybe I should write base down here so you know that there was base present. Otherwise, you'd assume the conditions are acidic. Why would you assume the conditions are acidic? Because it generates HI as a byproduct, but they make sure you don't build up HI. They throw in 2 equivalents of a pyridine derivative. and then you just pull that proton off. Now I've got more than one way to draw this out. I could just break this bond here to the HO bond and give the electrons to O minus, but I'm going to use those in this depiction to push this out in a single step. I could do that in 2 steps, and I would give you credit for that. It's hard to know the ordering of those events. Does the iodide leave as you're pulling the proton off? Oh, you know what? I can't get to that structure with that arrow pushing. I am sorry. We've got to go back here. I can't. That's not what my arrow pushing says. My arrow pushing says, sorry, this is not what, I'm doing the wrong order here. I can't get to that product. What I have to do is I have to kick out this iodine leaving group before I deprotonate that. And then we'll pull the proton off in the last step. Sorry, anything I said before, make your mechanism match this, because under the conditions of the reaction, it's more likely that the iodide will leave first. And it gives you, so now we're so close to this P double bond O, you could have written resonance structures over here. This is what I was getting excited about, is the P double bond O, right? You could have written resonance structures using this. Don't do that. And I was starting to get overly excited about that P double bond O. You can see it's coming. Let's go ahead and pull that proton off. And now we get this really stable, this super stable phosphorus oxygen double bond, a phosphine oxide. So that's the second part of this DNA synthesizer, You do fast exchange, 1 minute, 99.9% yields, but your product is a label phosphite, and then you oxidize it to a phosphate ester, rock stable. Yeah?
If your halogen was chlorine instead of iodine, would you have to invoke that resonance in order to kick out that group?
No, chloride's still a great leaving group. You know, like with acyl chlorides, we'll see more PCl stuff coming up soon in a second. Yeah, chloride is still good enough as a leaving group to leave easily from phosphorus. Oxygen, not so much, but chloride, bromide, or iodide, yeah, those bonds are really labile. Okay, so again, this chemistry of activating phosphorus by converting it into a phosphonium ion. You protonate it, you react with electrophile, and then it becomes much easier to attack. Okay, let's take a look at a different type of nucleophilic reaction of a phosphine lone pair, and this is called the Staudinger reaction of azides. I have to say the Staudinger reaction of azides because there is another Staudinger reaction that has nothing to do with azides. You can't just say Staudinger reaction and have people know what you're talking about. So, but when I talk about Staudinger reaction of azides, when I teach Chemistry 51C, the third quarter of introductory organic chemistry here at UCI, we talk about how to do SN2 substitution reactions with nitrogen. And the book introduces this ancient transformation called the Gabriel synthesis, where you use an imide anion. Don't know if any of you guys remember that, but people don't really tend to use that anymore. What people use as a nitrogen nucleophile nowadays in organic chemistry is people use azide anions as nucleophiles. There's no steric hindrance. You don't have to hydrolyze anything off. It's easy to convert the azide N3 group into an NH2 group. Boy, there's more than one way to do it. And one way to convert this azide, which you might have just made this through an SN2 reaction, this carbon-nitrogen bond. Now it's easy to convert that into an amino group. And so the Staudinger reaction is one way to do that. It involves a phosphine, and you have to have water in the mixture so you can get P double bond O as your driving force. Let's go ahead and take a look at the Staudinger reaction of azides. But I have to do something first. So the problem is, this is the resonance structure that 99.9% of people will draw 99.9% of the time for an azide. It's the one that I draw. That's the resonance structure I draw. But 99% of the arrow pushing mechanisms don't use this resonance structure. So let's go ahead and draw up the resonance structure that's going to help us understand the reactivity of an azide. What I'm going to do is I'm going to give these lone pairs over here to N plus, like this, and then I'm going to push these electrons onto nitrogen. And the resonance structure that I draw here is going to look like nitrogen gas. Wow, you know what that's going to do? Attach to an amide anion. So we got a leaving group attached to a nucleophile. And that's the resonance structure that's going to explain most of what's going on in azide chemistry. Now, the question is, when I throw this in with triphenylphosphine, which is a nucleophile, what's it going to do? Is it going to react with the nitrogen gas part, or is it going to react with the nucleophile part? Well, it's going to look for an electrophile. phosphine will. So let's go ahead and take a look at that. I'll draw my triphenylphosphine down here, right? And I'm going to add that to that diazonium. Don't add to the N+. It's not a carbocation or a carbenium ion with 6 electrons. The N+ has 8 electrons. Don't attack the N+. I know you're going to want to attack the N+, that's why I'm saying that. But don't attack the N+. You know, when we teach introductory organic chemistry, we talk about arene diazonium ions and electrophilic aromatic substitution. And you learn there not to attack the N+, man. That's total fool's gold there. We want to get rid of that N+ because nitrogen's electronegative, and the way we're going to do that is we're going to attack the nitrogen at the end and give the electrons to the N+. Now we know from stereoelectronics, we've talked about this before, when a nucleophile comes in and attacks a pi bond, the electrons appear on the opposite side. And so when we attack this pi system here, the new lone pair appears over here on the other side of where that triple bond used to be. So we're going to get an arrangement here of lone pairs that are cis to each other. Right? You started off with a lone pair that was sticking out here, and the new lone pair ends up here. The new lone pair ends up on the top. And that cis conformation, that syn orientation of these two groups, makes it very easy now for this nitrogen to be close to the P+. Right? Take your eyes off the lone pairs and look at the substituents down below. And so now you are perfectly set up. You're just perfectly set up now for this nitrogen lone pair to add into that phosphonium. Remember how we said it was easy for nucleophiles to add to phosphonium groups? We're perfectly set up for that. Now, I realize that 4-membered rings are not great, but you know, those things are right next to each other, nucleophile, electrophile. So it should make sense to you that the nitrogen should attack that phosphonium to generate this 5-coordinate phosphorane. Don't freak out over 5 single bonds to phosphorus. That happens all the time. We've been seeing these phosphorane intermediates with 5 bonds to phosphorus. Now I hope you can see as easily as I can that there's nitrogen gas, there's this strained ring here. We're going to break that strained ring and we're going to release nitrogen gas. Boy, that's looking pretty good. They've got a lot of things going for that arrow pushing mechanism. And where I start the bond, the arrow pushing is not that consequential. I just want to make nitrogen gas here. And I'll draw it like this. And so that's going to lose nitrogen gas. Super favorable. That's super favorable. And it's going to generate this iminophosphorane. Look at this thing here. It's an iminophosphorane. That. Now, that's not totally happy yet. Phosphorus wants double bond O, not double bond N. It wants double bond O. And so normally what you do is you take this iminophosphorane and you either have water present during the reaction, that's more typical, or you could come in and add water later, but most people do this in the presence of water, and I'm not going to draw out all the mechanisms. You can kind of guess that the nitrogen is going to get protonated, but you're going to end up making phosphine oxide as the leaving group, and that you throw that away. Nobody cares about that. It's a stable PO bond. People just care about the amino group, and that's what you want from this reaction. Now, there's another resonance structure I can draw for this iminophosphorane. Right? If I give the electrons to the electronegative atom in that group, that iminophosphorane really looks kind of like a phosphonium attached to an amide anion. And that amide anion is nucleophilic. If you do this inside of a cell, this was the basis for the Nobel Prize last year. This reaction was the basis for the Nobel Prize, the Staudinger reaction. Carolyn Bertozzi at Berkeley realized, you know, if I can sneak a phosphine into a cell and express some protein or something, trick a ribosome or trick the cellular machinery into expressing proteins or nucleotides that have azide groups on there, I can get phosphines to go into the cell, attack every azide group, and generate species that are nucleophiles. Amide anion nucleophiles, you can generate them inside of a cell using this combination of an azide group and a phosphine group. And you can get these amide anions, these iminophosphoranes that come from a Staudinger reaction to attack, make stable bonds, to hook together fluorophores, kind of surgically mess around with what's going on inside the cell using this Staudinger reaction. So You know, buried inside all of these simple looking reactions, there's cool ideas for you to explore. And maybe the next Nobel Prize is just waiting for you. Who knows what combination of chemistry. All right, so probably one of the most common phosphorus, this is probably not the most common phosphorus, but a super common phosphorus reagent that you will see in an introductory course are Wittig reagents, phosphonium ylides. And there's two different ways that we draw phosphonium ylides. Sometimes we draw P double bond N like this, where we draw a lone pair on the carbon and then a phosphonium group like this. And sometimes we draw it with this phosphorus carbon double bond. And both of those are fine representations. You know, it just depends on how willing I am to draw a bunch of lone pairs. This depiction right here is a phosphonium ylide. We refer to both of these as phosphonium ylides. Even when we don't draw P plus and C minus, we still call that a phosphonium ylide. The ylide form, the ylide resonance structure is so important. We still refer to this as a phosphonium ylide, even though we're not depicting it like that. And the bottom line with these Wittig reagents is they want to form P double bond O. Right? They want to form P double bond O. The carbon is nucleophilic because it's kind of like a carbanion, so you should kind of guess that it should look like this. This is what you should remember from an introductory organic chemistry course. You use that carbanion to attack the carbonyl. Instead of giving the electrons to the oxygen, you use the electrons to attack P+. And this is a concerted process. It leads to a four-membered ring intermediate that I'm not showing here. So there's a four-membered ring. I better draw that somewhere. Sorry, I didn't draw the phosphooxetane. But you generate this phosphooxetane intermediate that probably freaked you out the first time you saw it because you weren't used to drawing 5 bonds to phosphorus. But now that we've seen all these intermediates that have 5 bonds to phosphorus, this phosphorine intermediate shouldn't look so weird. So these reactions proceed through this phosphorine intermediate. And if, again, that phosphorus really wants double bond O, so we're going to take these electrons and push them into phosphorus here. Whoops, let me use my red pen, that red depiction. And then we're going to do this over here. So I should have drawn that intermediate in there. I'm sorry I didn't do that. Oh, look at that P double bond O, massive driving force. And this turned out to be a key reaction oh, I've got that drawn down below. What am I thinking here? Whatever, I've redrawn it. It's always good to draw phosphorine intermediates. Let me go ahead and push the arrows using this other resonance structure where I have P double bond C, right? It looks a little bit simpler. You know, that's a crummy stop. That's a crummy looking arrow because I'm super picky about the way I start my arrows. Arrows start with electrons. So let me make that arrow start from the middle of that P-C bond. That wasn't close enough to the middle of that bond to make me happy. Your arrows should start from the middle of bonds, the middle of pi bonds, the middle of sigma bonds, the middle of triple bonds. I didn't start that arrow close enough to the middle of the bond. And that makes this four-membered ring phosphorane. It's a phosphorane because there's 5 bonds to phosphorus. It's a phosphooxetane because oxetanes are four-membered rings with oxygen. There's a phosphorus atom in there. And let me just do the arrow pushing again using my beautifully rendered drawing that I have down here below. I could start my arrows with the PC bond, right? Or I could start it with which one you draw first. Nobody will know which one you drew first. And the reaction is you relieve ring strain and you generate P double bond O in the same reaction. Now, where do you get these phosphonium ylides from? I mean, this is kind of the downside to this reaction. This is the pain in the rear. You're kind of limited here about what kinds of Wittig reagents you can make. Because the first step in making a Wittig reagent is an SN2 reaction. And SN2 reactions are not great. So if you've got a hot electrophile, like a primary alkyl halide, you can do this. So here's an example with bromomethane. That's probably not the most convenient version because bromomethane's a gas. Iodomethane might be more common. But it's not easy to do SN2 here, right? And this has all the advantages going for it, right? You can't do competing E2 eliminations because methyl bromide has no beta hydrogen, so all you have to do is heat it as hot as you need to, and you don't have to worry about competing eliminations. But it still takes 2 days. SN2 reactions are not great, but this is the way you have to make these Wittig reagents. Now after you do that, you can't just come along with a weak base to pull off these protons here. The protons that are next to that P plus are not as acidic as the protons that are next to a typical like carbonyl group. And so you need powerful bases. There's only two common bases that we would typically teach you about for deprotonating. One of the most common is butylithium. Right? You might think, oh, I should attack the P plus with butylithium, but that's not as fast. Butylithium is not just a nucleophile, it's also aggressively basic. And so this is acidic enough that you deprotonate faster than you attack the phosphonium group. So the other common base that you'll see sometimes used here is something called dimsilanion. We'll talk about that in the next section on sulfur chemistry. And those are the only two common bases for deprotonating this. Not hydroxide, right? Hydroxide has an oxygen. That's going to bond to phosphorus. Not T-butoxide, that has an oxygen. It's not going to, and sodium hydride is too insoluble. You don't get good kinetics with sodium hydride. So butylithium is common, and that's how you make these Wittig reagents. You do a crappy SN2 reaction, and then you do a deprotonation using reagents that seem like overkill, but you have to avoid oxygen-type bases usually. Yeah.
You didn't have that organolithium in solution to the bromide attack the phosphorus group?
So the question is, would the bromide attack the phosphorus group if it was just sitting around? And no is the answer. I think there's unfilled orbitals on this phosphonium group here, and so I would guess that the lone pairs on bromine might want to be hanging out close. But if you put bromine on there, the bromine would get kicked out. The bromide is a good enough leaving group that the bromide would leave and give you a phosphonium bromide. And so these are not neutral phosphoranes. They're salts that have Br minus. If it was oxygen, yeah, oxygen phosphorus, man. That's where it's at. Okay, phosphorus functional groups are among the most common in organic chemistry and in biochemistry and in biology and in genetics. I mean, most geneticists and biologists are talking about A, G, C, T, G, C, G, and it's all linked together by phosphate groups. And that's typically not covered when you take an introductory class as the chemistry of phosphoryl substitution. So I've drawn out here a typical phosphate, phosphorus 5, or functional group here. This would be a triphosphate, as it's commonly termed. You've probably seen a lot of reactions of triphosphates, nucleotide triphosphates that act as subunits for nucleotide synthesis by polymerases. DNA polymerase uses these, RNA polymerases uses these, right? Nature doesn't use that phosphorus 3 trick. Nature makes bonds to phosphates right off the bat because enzymes can really facilitate substitution at phosphorus 5, whereas chemists use this phosphorus 3 trick. Now, what's the tricks that biology uses inside the active sites of polymerases or inside of a protein kinase? It's the same deal. The leaving group is not tosylate. The leaving group is not a chloride. The leaving group that's used universally by all enzymes that substitute at phosphorus, or pretty much universally, is this magnesium phosphate leaving group. So normally you have negative charges on these phosphates, but nature neutralizes that to make that a better leaving group using a magnesium ion. And there is no enzyme, right? All polymerases use magnesium for this reason. All kinases use this kind of a leaving group, or enzymes that process diphosphate leaving groups on prenyl groups to assemble terpenes, use magnesium diphosphate leaving groups. So this is the typical arrangement inside the active site of a polymerase enzyme, and you'll have some sort of a nucleophile, like the end of a DNA chain or a protein side chain, that can now come along and push out this leaving group. And you don't get it's not SN2, you push the electrons to oxygen, and then in a second step, the PO bond will leave. And because the OR group is coming in from the backside of the leaving group, many people would say, oh, that's an SN2, but it's very hard to distinguish whether it's an SN2 or goes through a phosphorane in those cases. So this is the most common mechanism for substitution. And I have to tell you, I just marvel at this, because substituting at phosphorus 5, that just ain't easy. Man, it is not easy. Why is it so hard to attack this type of a group. We refer to this as a phosphate diester. And at pH 7, it mostly exists like this with a negative O group on there. How are you going to get your crummy oxygen nucleophile to attack that when it's already got oxygen substituents on there? There's no driving force for that. So it's really hard to attack phosphate diesters. If you put a phosphate diester, like the backbone of DNA, in neutral water, the half-life is over 100,000 years at pH 7. Nature was really smart to make the bonds in your DNA out of phosphate diesters. Esters, the half-life is like less than a year at pH 7. You don't want to make DNA using carboxylic acid ester bonds. So this was the right choice for assembling your genetic material and keeping it together. It is not easy to use oxygen to attack phosphate esters that already have oxygen on there. You don't really have a driving force. Let's take a look at what it would take you if you wanted to hydrolyze a phosphate ester. Suppose you took hydrochloric acid and you put it in with a phosphate ester here, and you had water as your solvent, right? That's the conditions we use for Fischer esterification. That's the conditions we use for hydrolysis of esters. We use a strong acid like sulfuric acid or HCl. We use water or alcohol as the solvent. And what's the first step in this mechanism? It's just like a Fischer esterification. You use the lone pairs on this oxygen. That makes sense because it's kind of like P plus O minus, and then you pick up a proton from the acidic environment, either from H3O plus or from HCl. You don't know what's transferring the proton to there. And that makes it a little bit easier to attack the phosphorus. Makes it a little bit easier. It doesn't make it totally easy, but it makes it a little bit easier. And so if you look at the mechanism, right, what's the mechanism for attack here? Well, there's not a lot of hydroxide anion floating around in there. The best nucleophile you have under these conditions really is going to be H2O, is just going to be neutral water. So the only thing really that's there to attack is neutral water, not HO minus. So we're at an immediate disadvantage relative to an enzyme active site. Enzymes are great at having acids in one position and a nucleophilic hydroxide in another position, really close, and we can't duplicate that in an organic reaction where things are just floating around. So that's what makes enzymes special. So if you draw out the mechanism here, the mechanism for substitution would be this. Right? And there you go, you formed a new oxygen phosphorus bond, and then there's some more proton transfers. But with this molecule, it is so hard to add to phosphorus 5, that already has phosphorus oxygen bonds. It is so hard. 50% of the product comes from a different mechanism. There's a different mechanism for forming this product. And I don't know why I ended up with the 3R. I'll have to fix the product in just a second. Let me go ahead and draw out this, the other mechanism. Half the product in this reaction comes from this alternative mechanism. And let me fix my my product structure here. This was not supposed to be OR. This is supposed to be OH when you hydrolyze that. And so what's the mechanism for generating this diphosphate? What's the mechanism? It's 50% of the reaction comes from making a new bond between the water and phosphorus here. The other 50% of the product that arises in this reaction mixture comes from attack at carbon, not at phosphorus. It is so hard. Let me make that arrow end in a different way. It is so hard. Whoops, that's not what I wanted. It's so hard to add to that phosphorus that half the product comes from attack at carbon. In other words, the phosphate acts a little bit like a tosylate leaving group. Right? Tosylate, you make a tosylate leaving group because it's hard to add to the sulfur. You end up attacking at carbon, and the whole tosylate acts as a leaving group. So this just kind of shows you how hard it is to add to phosphorus 5 that already has 4 bonds to oxygen. Right? You've kind of reached the best kind of bonds that they want to have. So, okay, so very hard to add to phosphorus 5 that has I guess 5 bonds to phosphorus. So you end up seeing substitution at the carbon atom, and you'd end up with less than 50% of the. They both of these mechanistic arrow pushing give the same product. So if you don't isotopically label your oxygens or do some trick, you wouldn't know that those two mechanisms are simultaneously going on in the same reaction mixture. And remember, in my class, I don't ask you what is the mechanism for this reaction. I ask you what's a plausible mechanism. So you could draw either of these mechanisms, and you're right. Sometimes there's two different pathways generating product in the same reaction mixture. Okay, how are you going to get substitution at phosphorus 5? Well, what you want to do is put crummy bonds on the phosphorus. Bonds to chlorine, bonds to bromine. Right? Those bonds are going to be easy to break. Thermodynamically, that's not downhill, to have these phosphorus-chlorine bonds. We really want to have oxygen bonded to phosphorus. So let me show you one of the most reactive phosphorus reagents that you commonly see. And this is a reagent you should have seen in an introductory organic chemistry class. It's POCl3. And again, look at those chlorines. You know those want to be substituted by oxygen, or if they could, at the end of the reaction. And so this is a reagent combination that you should have seen used for eliminations, POCl3, and we call this POCl3 in the lab, just as nobody calls it phosphorus oxychloride or whatever. I don't even know what the IUPAC name is. So POCl3 is easy to attack because of those chlorines. Oxygens have no problem. This phosphorus atom is just inviting that alcohol to attack. Let's go ahead and draw out the mechanism for this process. Of attacking. Boy, does that phosphorus want to have oxygen bonded to it. So we're going to start off the mechanism. We're going to push the electrons up to the oxygen atom, and we're going to make a phosphorane intermediate, just like we've done over and over again. I'm not going to show the mechanism because we've drawn enough of these substitutions via phosphoranes, 5 bonds to phosphorus, 5 single bonds to phosphorus. I'm not going to show that. I'm just going to take you to the next intermediate, which is going to be a chlorophosphate ester. Right after all the dust settles and and you've substituted one of those chlorines, it's just like an acyl chloride, acid chloride mechanism. You end up with an intermediate that looks like this. And that's a good leaving group. So when you do these reactions using pyridine as a solvent, in theory the pyridine could attack the phosphorus, but phosphorus really wants phosphorus oxygen bonds. Nitrogen, not so much. And so when you're stirring this around with pyridine, I guess I could just write base. I don't know why I'm drawing the pyridine molecule here. And that can just do an E2 elimination mechanism. And this is a common reaction used to eliminate alcohols without going through carbocation intermediates. Right? One of the first reactions you learn for elimination is you just dump in a bunch of acid and heat it. Well, a lot of compounds will rearrange, or the double bond will shift around because the carbenium ion does 1,2H hydride shifts. And so this will give you clean E2 elimination mechanisms. And I've picked a substrate here where if the oxygen is in the middle, you can't tell which side you eliminated from, right? Half of your product has the double bond here, but that's the same product. Okay, so not easy to attack phosphorus 5 when there's all oxygens on there, but when there's chlorines on there, man, POCl3 is reactive. That is a hot reagent with those chlorines on there. And so it really wants to form bonds to oxygen. Let me show you one last reaction that involves a phosphorus reagent, and it's POCl3 again. This is one of the common reactions that you'll see people present in a class like this, and it involves POCl3 and NN-dimethylformamide, which is a common solvent. But the key reagent that you're generating is this chloroaminium species right here. It's this chloroaminium, that. Now, where do you get that, right? Why are people doing this reaction? You use this reaction called the Vilsmeier-Haack reaction. You use it because you cannot commercially buy, for electrophilic aromatic substitution, for Friedel-Crafts, you can't commercially buy acyl chlorides when it's an H. You can buy it when it's a methyl, acetyl chloride. You can buy it when it's a phenyl, benzoyl chloride. You can buy it when it's an alkoxy group. It's called a chloroformate, chlorocarbonyl methoxy, isobutyl chloroformate, anything but an H. So if you want to do Friedel-Crafts acylations when R is an H, you're kind of out of luck because you can't buy that acyl chloride. And so that's why they use this Vilsmeier-Haack reaction. You're going to have to make something in the lab. And so here's the reagent they use. Instead of using a reagent you can't buy, I'll just write unstable here. I'll just tell you, it decomposes to give carbon monoxide. I'm trying to write unstable. I'm running out of room. Let me write it on the other side or in red. So you use this reaction because this acyl chloride is unstable. It generates carbon monoxide and HCl. So that's why you use this Vilsmeier reagent up above, a chloroaminium ion, instead of an acyl chloride. And you typically do this on activated aromatic rings, not on deactivated ones. That really doesn't work. And so it ends up not generating a carbonyl group at first. What it does is it makes a new carbon-carbon bond right here, but you have an aminium ion on there. But that's no problem. When you just dump in water with your workup, it hydrolyzes spontaneously to give you the C double bond O that's thermodynamically favorable. So let's take a look at how you use POCl3 to generate this chloroaminium species. So what you do is you take DMF, you can use it as the solvent here for the reaction, and when you add POCl3 to that DMF, it's the oxygen end of that DMF that's going to act as the nucleophile. So let me go ahead and start my arrow pushing with this nucleophilic nitrogen, but it's the oxygen atom that acts as the nucleophile. I'll take these electrons and push them into the carbonyl. That's why the oxygen is nucleophilic. Amide nitrogens are not nucleophilic. It's the oxygen atom of amides that's nucleophilic. And we know oxygen wants to be bonded to phosphorus, and so we just attack here. And we need to push the electrons on P double bond O on that oxo group up to the oxygen. And so that generates this pentacoordinate phosphorane intermediate. Like we've seen a bunch of pentacoordinate phosphoranes in here. And so, we can draw, you end up with this species here where you've got a leaving group now and an O minus on that phosphorus. So I hope it makes sense that we're going to push out one of those chlorides out of the phosphorus. So let me go ahead and push these out. I've kind of drawn this as a trigonal bipyramidal structure. You make the ligands leave from axial positions always, from trigonal bipyramidal intermediates. And so you generate this type of dichlorophosphate group here. And this whole thing here, this whole species right here is a good leaving group. And so we're going to end up using that as a leaving group. Not in an SN2 reaction, but that's going to walk away with the phosphorus now bound to the oxygen. So we have this chloride counterion in here that's going to attack the aminium ion. Boy, it's so easy to attack aminium ions. And that will generate this system now. It'll generate this species where we've got lone pairs on the nitrogen ready to push out this leaving group, this dichlorophosphate anion leaving group. So let's go ahead and use those lone pairs on that nitrogen. We'll push down. Well, let me push this is good. And I'll give the electrons to that phosphate. And so you'll have your counterion that's floating around throughout the reaction now is this dichlorophosphate, and it doesn't have 3 bonds to phosphorus, but it does have 1, O minus, and so that makes it pretty happy. And so now this will be hanging out throughout that whole Friedel-Crafts acylation reaction, and the chloroaminium can do its job of making a carbon-carbon bond through electrophilic aromatic substitution. So this is referred to as the Vilsmeier reagent. It's actually the salt, and you use it for Friedel-Crafts acylation reactions. All right, so that's phosphorus. Phosphorus loves bonds to oxygen. If you want to do substitutions at phosphorus, man, phosphorus 3 is what you want to be doing. And you want to be making phosphorus-oxygen bonds. That's kind of the thermodynamic sink for phosphorus chemistry, is to make phosphorus-oxygen bonds. And unless you're an enzyme, I would not be trying to do substitutions of phosphorus 5 that already has 5 bonds to oxygen, because you've got nothing to offer there. That's not easy. All right, when we come back on Wednesday, we're going to start sulfur. We've got 2 more lectures on sulfur chemistry and plenty to talk about there. That's kind of covering some ground we've already mentioned, but making it a little more complete.